method is used to generate numerical approximations for solutions to differential equations that are not separable by the methods tested on the AP exam. It is necessary to be given an initial point and a rate of change, or the derivative of a function. Euler's method uses locally linear approximations as successive steps to estimate a solution. So we are required to have the initial point, the derivative of the function usually given implicitly, and the differential increment for x, or the change in x in steps. Given the differential equation dy over dx equals x plus 2, an initial condition of y of 0 equals 3, find an approximation for y of 1 by using Euler's method with 2 equal steps, and sketch your solution. So the very first thing you should do when approaching these questions is make a table. So your table should include your initial condition, x comma y, which in this case was y of 0 equals 3, so 0 comma 3. Then you should have your change in x, or step size. In this case, your step size should be 1/2 because you're trying to go from x equals 0 to x equals 1. Next, you should find your dy dx. In this case, they tell you that dy dx is 0.5, or 2.5. Our change in y is going to be 2.5 times 1/2, which is going to be equal to 1.25. And our new point in this case is going to be 1, 5.25. So let's look back to what they asked us in here. Find an approximation for y of 1 by using Euler's method with 2 steps. So this is our approximation. Y of 1 is equal to 5.25 by using Euler's method with 2 equal steps. And they also asked us to sketch our solution. So if we sketch these 2 points on an xy plane, we should get something like this, with our endpoint being 1, 5.25. This part of the question is a flashback to Calculus AB, where we learned how to solve differential equations. So it asked to solve the differential equation dy dx equals x plus 2 with the initial condition y of 0 equals 3, and use our solution to find y of 1. So the first step we must do is recognize that we are given the slope here. So in order to find the differential equation, we should take the integral. So the integral of x plus 2 is equal to x squared over 2 plus 2x plus c. And if we plug in our initial condition of 0, 3, we get that c is equal to 3. So our answer is x squared over 2 plus 2x plus 3. And they ask us to use our solution, which is right here, to find y of 1. So y of 1 equals 1/2 plus 5, which is equal to 5.5. Now we're going to look at the error in using Euler's method. So the error is defined as the difference between the approximate value and the exact value. So in part A, we found the approximate value using Euler's method with 2 equal steps. And in part B, we found the exact value by solving the differential equation and using our solution to find y of 1. So now we're going to calculate the error in our answer and look at how we can produce a smaller error. So to calculate the error in our answer, all we have to do is take our exact value, which was 5.5, and subtract our approximation, which is 5.25. So we get an error of 0.25, or 1. Calculator. So for my calculator, I have a TI-84 plus CE, and I downloaded this Euler method program, which is very useful. So all you have to do for this is give your dy dx, which is x plus 2, your x step, which we identified as the change in x, your initial condition, your end condition, your initial y value, and then it not only graphs it for you, but it tells you what the approximation is. So this is a very quick way to do it on a multiple choice section of the test. Now we're going to look at a practice multiple choice question for Euler's method from a previously released CALCBC exam. We are given, let y equals f of x be the solution to the differential equation dy dx equals x plus y with the initial condition f of 1 equals 2. What is the approximation for f of 2 if Euler's method is used, starting at x equals 1 with a step size of 0.5? So the first step is to make the table with our initial condition, our change in x or step size, dy dx, which is given to us, our change in y, which is equal to dy dx, times change in x, and then our new point, x plus change in x, and y plus change in y. So our initial condition is 1, 2. Our change in x is given to us as 0.5. Our dy dx can be calculated as 3. Our change in y is equal to 3 times 0.5, which is equal to 1.5. And now we can calculate our new point. X plus change in x is 1.5, and y plus change in y is equal to 3.5. So since we're asked to find the approximation for f of 2, we have to do 2 steps of this method. So the next step, our initial condition will be 1.5, 3.5. Our change in x is constant as the step size. Our dy dx in this case will be 5. And our change in y will equal 5 times 0.5, which is equal to 2.5. And therefore, our new values for x plus change in x and y plus change in y will be 2 if Euler's method is used, starting at x equals 1 with the step size of 0.5. So we can say that our approximation of f of 2 is equal to 6, which is answer choice C. The first thing we're going to do is make the table with the initial condition, change in x, dy dx, which in this case is equal to 2y minus 4x, change in y, which is equal to dy dx times change in x, and our x plus change in x, comma, y plus change in y. So once you make this table, you're going to go find all these pieces. So x comma y, the initial condition, in this case is 0, 1. Our change in x is our step size, which is 0.1. Our dy dx is 2 times 1 minus 4 times the first step of our Euler's method for this equation. So the next step will be as this, the initial condition, 0.1, 1.2. Our change in x is still 0.1. And our dy dx is 2 times 1.2 minus 4 times 0.1, which is equal to 2. So our change in y is going to be, again, 2 times 0.1, which is equal to 0.2. And our x plus change in x is now 0.2. And our y plus change in y is 1.4. Response question. This is from the 2007 AP Calculus BC exam, and it's question number 5, and it's question number 6 on the worksheet. So it states, let y equals f of x be the particular solution to the differential equation with the initial condition f of 0 equals negative 2. Use Euler's method starting at x equals 0 with the step size of 1/2 to approximate f of 1. So the first thing that I'm going to do is make the table with my initial condition, change in x, change in y, dy dx, and then x plus change in x and y plus change in y. So you can see here, if I plug in all my values, my initial point is 0, negative 2. My change in x, or step size, is 1/2. My dy dx, in this case, is negative 3. And therefore, my change in y is negative 3/2. So I'm going to take the point 1/2, negative 7/2. And I'm going to do the second step of Euler's method for this problem. So my change in x is still constant at 1/2. And my dy dx, in this case, is going to be negative 9/2. So therefore, my change in y is going to be negative 9/4. So my new value for x plus change in x and y plus change in y is going to be 1, negative 23/4. Part B of this question states, let y equals g of x be another solution to the differential equation with the initial condition g of 0 equals k, where k is a constant. Euler's method with the step size of 1 starting at x equals 0 gives the approximation g of 1 is approximately 0. Find the value of k. So we're going to make the table that we always make with our initial condition, change in x, dy dx, and change in y, and our new point, x plus change in x and y plus change in y. So our initial condition is given as 0k, so we're going to plug that in here. Then we're going to find our change in x, which is our step size, our dy dx, which is 3x plus 2y plus 1. So if we plug in k as y, we get 2k plus 1. And therefore, our change in x is 2k plus 1. So plugging these in, we get x is 1, and y plus change in y is 3k plus 1. So it asks you to find g of 0 is approximately 0. So all we have to do here is set our 3k plus 1 equal to 0, because that's our approximation, to find k. So we get that k is equal to negative 1/3.